Great, so welcome back. We're going to have 2 talks and then we'll break for lunch. Lunch will be provided here in this room. First, in this next session, we're going to hear from Xiaodi Wu, and he's going to tell us about quantum query complexity of entropy estimation.
Okay. Does the mic work? Okay. Yeah, thanks for inviting me here. So I actually recently joined the University of Maryland in this Quick Center. Just for a little advertisement here, I think you're all welcome to visit us at some time. And so actually, I feel very honored to give a talk in this venue, especially for a topic that I just, this is my first work on quantum algorithm. It's type of algorithm. And before I really talk about what I have done, I want to give you my own motivations of why I choose to work on this type of problem. So actually, I start all this kind of work by first reading a survey on quantum property testing by Montanaro and Dove. So thanks for the survey, yeah. So I found this is very interesting. It's a topic which is actually classically there are a lot of research going on. But we have seen lots of examples can be characterized as property testing, but there's no very serious study of this topic. And this is the main motivation. And we start with something simple. We say, how about we try to start quantum testers of classical properties? And moreover, I choose to work on the testing of distributional properties. Again, it's a well-motivated topic in the classical literature. And moreover, if you maybe attend the talks in the previous 2 days about machine learning, so distributional property testing is quite similar to, say, if you have like a latent model in machine learning, you want to learn about those parameters, or you want to just tell which case it is. So it potentially has connection to the learning problems as well. I think it fit in this theme. And the third one is that the objects are distributions. They're not Boolean functions. So we have seen a lot of results on Boolean functions. The distributions might bring new insights or call for new techniques. So these 3 points motivate me to study this kind of question. And of course, when we try to choose one question, you got to start with something concrete. I think I start with something that is quite well known. It probably is the most easier one, the easiest one to introduce. So my problem is that I'm talking about estimating entropies of any distribution. So I guess the audience here are probably familiar with this concept, but just quickly go through it. So for any distribution, the Shannon entropy is defined in this form. It actually captures like the uncertainty or maybe randomness of this distribution. And important generalization of the Shannon entropy is the Renyi entropy. It can be defined for any positive alpha. And when so this is the general distribution for the Renyi entropy. And when alpha goes to 1, its limit becomes the Shannon entropy. So those 2 are very important quantities in information theory. And also you can use that to characterize many properties of distributions. So a natural question in this property testing literature is basically say, if I give you samples independently drawn from this kind of distributions, I want to estimate this entropy or, the Shannon entropy or Renyi entropy within some error with high probability. I want to determine what's the smallest number of samples that I need for that purpose. As I said, this is a theoretical appealing topic, and also it's very clean. It has an intimate connection to statistics, information theory, learning theory, and even algorithm design. So the question we're asking here is that, is any quantum speedup for this task? As I said in the very beginning, I think this question aligns with the emergent topic called quantum property testing. But this one focuses on distributional property. So the first paper, to my best knowledge on this topic, is by Bravi, Harrow, and Hestim, which they've studied the quantum speedup for testing distribution property like uniformity, orthogonality, and statistical difference. This also one of follow-up work, I think, by Chara Borti, I think It's also involved of. Okay. So, what I want to say is that this is actually the only 2 references I have found. So we're the third one in the play. It's actually after several years we found this might be an interesting problem to explore further. So what's our main result? So before talking about our result, let's just tell you a little bit about what's the classical result. So this is a well-studied problem. So you can imagine classically this sample capacity or number of the independent samples. There's tidal bounds already being explored. But actually, this has been discovered in information community first, and then discovered by the theoretical computer science community, where they use different kind of error measure and also care about different parameters. Or some community they don't really care about log term, but some do care. So for Shannon entropy, the best bound so far. So this is the Valiant brothers. Is in theoretical computer science community, and this is for the information theory community. They all get this same bound. It's almost just linear, but it's linear n over log n. And for general Renyi entropy, the story is a little bit more complicated, but basically you divide this all possible alpha into 3 different parts. The parts between 0 and 1, the parts that are bigger than 1 but not integers, and part that is integers. So we'll see more clearly with the picture in after the slides. But what you can see is that when alpha is between 0 and 1, it should be superlinear, and when alpha is non-integer, it's almost linear. And when alpha is 8 integers, then you can get something better. So here's the list of our result. So this is the classical one I just showed, and this is basically all this result we have in talk about in this talk, and also this the work in the first coming paper. So basically, we give all this quantum upper bounds and also lower bounds for all different range of alpha. So let me use this this picture to illustrate that. So you can just come back and forth to compare the result. So let me just describe this figure. So what does it mean? So this x-axis are this alpha, and this y-axis represents this exponent of n for the algorithm. So say if you look at y being 1, that means linear. If anything below this means sublinear, and this is a superlinear. And the green line are the classical bounds, because it's both the upper bounds and the lower bound. So you can see for any alpha bigger than 1, it's almost linear, except for those integer points, which you can do something better. And for anything smaller than 1, you have a superlinear function like this. So our upper bounds, quantum upper bounds, is the red line. So we still have similar shift, but it's like for the interval between 0 and 1 is it's shifted down. So you see that's the quantum speed up, because we can get some sublinear even for alpha between 0 and 1, and we can get all speed up. Eventually it's just not much speed up when alpha goes to infinity, but it is just strictly sublinear for any alpha. And for integer alpha, we can do slightly better than the classical algorithm as well. We also prove the quantum lower bounds, which is illustrated by the pink line. And we, combining our upper bound and lower bounds, we have shown for estimating the Renyi 2 entropy, which is the collision entropy, we have a tight bound that's a cube root of n. So just coming back to maybe this table. So this is the precise bound we have shown. So as I said, for alpha equals 2, we have the tight bound like this. It's a cube n capacity compared to classical, the square root of n. For Shannon entropy, that's alpha equals 1. We have a square root of quadratic speed up versus the classical bound. And for all the others, since we have lower bounds, there's still a gap between our upper bound, between in our current result. So I have actually give a similar talk in Microsoft Research in April. So if you happen to sit in this in my talk in April, so this is actually the picture I gave back then. So the only difference is that we have improved our result for general alpha case, where this is what we get for in April. We only have the quantum speed up within very small range of alpha. Now what I can show is you can achieve actually quantum speed up for all possible alphas. Okay. So any questions so far? So let's talk a little bit about the techniques. So in the high level, before I really want to talk about the technique, I want to mention there's a subtlety in the model. I mentioned that classically, you imagine when you really care about sample complexity, you have independent draws for some distribution. But if you want to allow quantum to have some advantage, you probably imagine you have some quantum coherent access to the distribution. But if you're giving classical independent samples, that just makes it impossible for you to have any quantum coherent access to the distribution. So one of the contribution by this BHHF work is they propose oracle model to describe the distribution. So precisely, just imagine there's an oracle function for any distribution, P over a discrete set. So it's a function mapping from a very large domain into N. N is the support of this distribution. And each PI will be just looking at the size of per image for each I and divide by the size of the input domain S. So S can be arbitrary. So for any this kind of oracle, for any distribution, there can be many oracles satisfy this property. And you can see here, so all this PI, there should be rational numbers. So we make another restriction. We're not really considering irrational distribution, but which actually is reasonable since you cannot really store irrational numbers on your computers. So if you just use this oracle and samples uniformly from this input, you look at output, you can exactly recover a sample that is drawn from the distribution P. So that being said, so this is a stronger model than the case when you only can get a sample from this kind of distribution. But why this is also a reasonable model? So one justification is that in BHH they show if you count the query complexity of this oracle model, basically the number of queries you make to this oracle, and also count the sample complexity in the model where you only use independent samples from the distribution, you can show they're actually equivalent, at least in the classical setting. So that's a justification of this model. And I think there's a further justification, which you can imagine in some application where the distribution actually generated by something like this. If you imagine you're in the algorithm, maybe your output is just some kind of distribution, and you want to distinguish which case it is. But the way you're generated outputs, it should be something like this oracle function. So that makes me think this oracle model can also be readily useful for algorithm design. If you have algorithm for this type of oracle model of the distribution. So that's what we are going to use in the quantum setting. So this, if you use the oracle model, then its quantum version is very straightforward. You just imagine you turn this function into a unitary, and you can make a query to this function by getting input S, and you observe as the output. And from here, we just need to care about the query complexity of using this oracle function. So here's the roadmap of our techniques to handle all different cases of alpha. We basically have 4 different cases, and I quickly just go through one by one, give you some high-level idea. So in the very, very basic high-level picture is that we try to give you a general distribution property estimation problem. So this is even more general than the real problem we want to solve. But the question is that you have some kind of distribution given by this oracle. I'm asking to approximate fp, which is some pi times fpi. So fpi can be any function. And we want to estimate this to some error with high probability. If we choose this fx to be log x minus log x, then this fp will be the Shannon entropy. So that's one case that we're thinking about. The other case will be if we choose fx to be x to the alpha minus 1, then this rating entropy will be proportional to the logarithm of fp. So if our final goal is to achieve additive errors for hp or h alpha p, then in the first case, we care about additive error for approximating this fp. In the second case, we care about the multiplicative error of approximating this fp. So what we have done is that we basically just formulate ideas in BHH and propose a simple framework for approximating this fp. So the idea is that you first just sample any I according to the distribution of p. So that's easy to do because you already have the oracle. You can sample any I like that. Then we use amplitude estimation. So that's the quantum thing. We estimate this probability pi. Output is estimated as the tilde of pi. And why we can do that is, again, by definition. So the pi will be the size of the pre-image over the size of the domain. So in order to approximate the pi, you just need to do some kind of counting. And we know, that's something you can do. There's a quantum counting algorithm. So you can output an estimation of the pi tilde, and then you output this fpi. So we have some further step to on top of the step routine, but it's easy to see if we just look at this part, the output of the expectation of x will be just summation pi fpi. Hopefully, if the pi tilde is a good estimate of pi. So the expectation of this subroutine A already is something we want. But you can imagine intuitively the performance of this algorithm will depend on its expectation as well as its variance, or maybe how concentrated this output distribution will be around its expectation. So of course we want the output this expectation is as close as possible to the real value we want to estimate, and also we want the variance small. So this, of course, is just one simple framework you can use. You can use in other framework. So the good thing about this framework is that it seems very intuitive. This might be the first thing you want to try, and you might thought maybe what's left is just do some calculation. Although you want to do the calculation of the expectation as the variance, that could be very, very tedious and complicated for different kind of f. But actually, if you just do that, you'll find out you only have very limited quantum speedup. You cannot achieve the whole speedup as illustrated in this picture. And actually, this is not really unusual. If you look into the classical literature, they have something like this, very basic estimator they're going to use. They only give you something in very limited speed as well. So you always need to have some new ideas and new techniques to handle, for the general case. So which I illustrate later. But so what's going on after the slides will be, I'll tell you first, if you just use this kind of framework, what you can do. And this is the case for the Shannon entropy. So if you just use this kind of framework, and comparing to what has done in BHH, we have two new ingredients. The first one is Montenero's algorithm for what calls quantum speedup of the Monte Carlo method. It's just imagine you have any quantum procedure. It has output x and has variance upper bounded by sigma square. And there's a quantum way you can leverage this circuit of A and A inverse. Only use just big O of sigma over epsilon that times of A and A inverse. You can output a very good estimate of its expectation. So this is a projected speed out over the best you can do in the classical setting, where you need to have sigma square over epsilon square. So we leverage this tool. So another tool we need to use is that we, for this particular function, fx equals minus log p, we need to have a fine-tuned analysis to bound the value of the log 1 of p when p is very, very close to 0. So So this is very unique to the Shannon entropy case. But basically just leveraging those two ideas as well as the basic framework, so this is what we can get. We can get a big O tilde of a square root of n query complexity for Shannon entropy case, which is quadratic speedup for over the classical one. But extending this idea to general Renyi entropy is troublesome. And that's what I'm going to talk about for general Renyi entropy. So why is it troublesome? The main issue is when we talk about the Shannon entropy, you're looking for additive errors. You're looking for additive error guarantee, and this is a good quadratic speedup by Montanaro algorithm. But for general Renyi entropy, you're actually looking for the multiplicative version of this concentration of major equation. And it turns out there's almost no speedup in the worst case if you look into what we know about this general problem. And if you just naively use the same framework, you only get a quantum advantage between half and 2 for this alpha. This is what we get in April talk, in the picture I have shown you. So what we have done in the past 2 months is try to get around of these obstacles. And here are a few new observations. So the first one is that we found out if we can in advance have some knowledge about where the expectation might be. Assume like expectation will be in some interval A to B, where B is actually just the big O of A. Then we can develop a variant of Montanaro algorithm with a quadratic speedup. But this observation by itself seems not very useful, because in that case, you already have some kind of constant error, multiplicative error version estimate of this expectation, because A and B, they're within constant factors. So this is by itself is not that useful. The second observation is that we think we don't know this A and B once, but how about we use something else to give you estimate for A and B? So we observe that if we look into the problem we want to estimate, basically this is the sigma I pi to the alpha, we look at this function for different alpha. So how about when we try to estimate the P alpha, can we estimate maybe P alpha prime such that the result of P alpha prime can help me to give this kind of interval for P alpha? So what we found is when this alpha 1 and alpha 2 are very close enough, within this factor, then if you have estimate of P alpha 2, then this will give you a very good estimate of P alpha 1 up to some interval, constant factors. And this can be fit into the first theorem and then give you some quadratic speedup. The question then reduces to how about you try to find some way to estimate P alpha 2. Again, this problem, it's a similar problem. So the idea is that we just recursively do this. And so every time we start with P alpha 1, we find a P alpha 2, and then we from P alpha 2 we found maybe P alpha 3, such that the sequence of this alpha will try to move towards 1. So why we want to move towards 1? It's because we already know when alpha is very close to 1, there's quantum speed up. So that will be the boundary case. But of course, we don't directly use this interval. You can even further make this speed up that procedure. So at a high level, what you'll see will be if an alpha is bigger than 1, you just keep multiply alpha with something smaller than 1 and keep going until alpha is very, very close to 1. And when alpha is between 0 and 1, you just multiply something and it keeps increase alpha until it's very close to 1. But if you do the calculation, because the factor we're using, you probably just roughly use big O log n cos of this procedure. And then by using this technique, and actually the analysis is not very easy to carry through, but you need to be very, very careful. But eventually you can get the speed up for all possible alpha. So one thing I want to highlight here is that if you probably have seen something similar before, either in simulating annealing, there's like cooling schedules, or maybe in value estimation of high dimension, convex body. There's some, this like a multi-section, multiplicative factors thing. I also the design principle actually very, similar. Although we didn't see those algorithms before we really have the solution, but then we find out there actually is something already there. But their difference is that we need to adapt this kind of design principle to our context. So I think this is something similar in spirit, but the techniques are still quite different in details. Now let's move to the remaining two cases. So there's another case about the integers, which we already see. Classically, you can have something better than non-integers alpha, and you can actually do something similar in the quantum setting. So why is that? So we can just look through the classical case and get some inspiration. So classically, when you try to estimate Rayleigh entropy for any integer alpha, this problem actually connects to something called the alpha frequency moment. So what's the alpha frequency moment? Just imagine you have like a sequence of those numbers from the domain n, and you count the occurrence of those numbers, and like them to be just m1 to mn. So this will be fk defined to be summation I mi to the k will be just the k frequency moment. And the key observation actually very easy to see is that, so this is the Rayleigh entropy definition, and this is what we get from the frequency moment. You see, they're same because you already know m. But just for information, this is actually not the best classical estimator. I won't tell you why, but you can imagine this is the empirical saying not always the best. That's same case in our quantum setting as well. So we want to leverage this connection. So instead of directly estimating this pi and estimating using our basic framework, we want to just estimating this alpha frequency moment. And fortunately, there's an algorithm of doing that. But there's two issues with executing this idea. The first one is that classically, in order to find this frequency moment, you need to know the histogram of your samples, and you need to choose m. And we cannot do that. We cannot just say generate those m, because in that case, you already have the same complexity as classical ones. So there's a trick that we make use of the structure of the quantum oracle. We just say, imagine now you give the oracle a different meaning. Now just say this is the input domain, but imagine this 1 to the s, just some sequence. And you seek this s. So all you want to do will be just get the alpha frequency moment of this, the sequence of applying this oracle to each of the element in the input domain. And you can get exactly something quite similar to what you would get with the alpha frequency domain if you have like m samples. And there's another issue is that if you use this idea, if put into the best quantum algorithm for alpha frequency moment, then you'll see the dependence is actually on s, not on n. So n is the support of the output domain, but the s is the size of the input domain. So s is actually some kind of irrelevant parameters. So what we have done, roughly is that you can replace s by alpha n in this particular algorithm and redo the analysis. It's not a black box way to set s to be alpha n, but somehow when you look into the analysis of the algorithm, and particularly for this problem, you can do that. And then we can somehow put this dependence on n, the right parameter rather than s. So finally, there's the case will be the mean entropy case. So mean entropy, you want to find maximum the probability of pi. And because we already have algorithm for general alpha or beta algorithm for general integer alpha, a natural guess will be you probably can choose some alpha such that which is integer, and this gives you some linear complexity, and use that as a good estimation for the h mean. So unfortunately, you cannot do that. The reason is that when I talk about the integer alpha, this big tilde of, the tilde of big O hides the exponential dependence on alpha. And when you try to use this approach, it actually can quickly go, beyond linear. So this is, false hope. So we actually develop another reduction. So the reduction, again, is to distinctness problem, but it's to the log n distinctness problem. So roughly, so what we have done, so we have used a technique in the classical literature called personalized sampling. So the idea is actually coming from how to divide the best classical estimators. And that's also the reason why I say the empirical estimator for random entropy is not the best one. You need to use some technique called personalization. And the end result will be you generate some Poisson distributions that is parameterized by the pi, and your guess value of pi, which are called lambda. And there's another fact is the log n is actually natural cutoff for the Poisson distribution. So it's actually independent of the problem, but I think it's a fact for the Poisson distribution. So the rough idea will be if this lambda times the maximum pi passes some certain threshold, basically you know that your mean entropy passes certain threshold, then with high probability, you can expect the occurrence of your samples will have a log n collision. And you can use the log n distinctness problem to find this collision. Otherwise, you maybe say, your lambda is not good, your guess value is not good, you just update your lambda and try again. So there won't be many tries of this lambda, so you're down. So the most costly complexity in this procedure will be the algorithm for solving log n collision problem. And actually, something I mentioned in the open question section. So I probably quickly skip the quantum lower bounds. So you see this, the pink line, which is not that satisfactory, but give you something. We obtain that by reduction and the polynomial method. So there are two questions I think this is very interesting, immediately raised by our current result. The first one is we show the reduction from to the mean entropy case estimation to the log n distinctness problem. And if you try to investigate the current quantum algorithm by Ibanez and the Beloves, put in this k equals log n, and then you see all of them, their algorithm don't give you any quantum speed up. But there's no lower bound for that case either. So you don't know what's the real case. And another open question I think is interesting is that classically when people design these estimators, there are actually many, many different kind of techniques. But in the quantum setting, we just try the one particular approach. And you can see quantum speed up, but we haven't really leveraged classical techniques. So can we leverage the design principle of classical testers into our quantum design? That's another question. And you remember there's still a gap between our, my quantum upper bound and quantum lower bound. And I think this is also interesting thing to explore. And thanks for your attention.
Great, thank you. Are there questions for Xiaodi? Yeah, Anders.
You showed this plot where the classical bound was tight, whereas your quantum upper and lower bounds only touch that single point. Mm-hmm. What do you think? Is your upper bound something that you should try to improve, or your lower bound in order to match the two curves?
Oh, and I think that's a very good question. I actually hope I can improve them both. So I think they should be meeting some middle point. But let me just quickly go back. This picture, we only have a tight bound when alpha equals 2. So what I want to say, I actually have two points on this. From the upper bound point, I don't think we have a very good understanding of what will be the right estimators. You see, we use very natural estimators. And classically, people point out issue with this kind of estimators. The main issue is that the natural estimators can cause some unexpected large variance. So you want to have the variance pretty small, then you need to use something not that natural. Somehow, by using the, I think, approximation theory or, using polynomial to approximate the function, something like that. And we haven't used any of this kind of idea for our upper bound. So that could be improved. And from the lower bound perspective, it's just that, so we obtain this lower bound by just reducing the problem to the pulling function problem. It's like collision, or maybe use the polynomial method for lower bound for the collision problem. But you see, what we really have is not really a Boolean function problem. You want to estimate this entropy and over distribution. So I just say, probably we just don't have the right tool for the lower bound either. So I always say, probably can improve them both, and you can have a better picture. Yeah.
Is there another question while Stephanie prepares? Yeah, great, Ronald.
What about the gate complexity of your algorithms?
Oh, gate complexity. That's, we really haven't really do the calculation, but you see our algorithm is simple. So that means the simple complexity or the query complexity is almost the running time as well.
Because it's all based on amplitude amplification.
Sorry?
Because it's all amplitude amplification, amplitude estimation.
Yeah, yeah, just that, and almost nothing else.
Okay.
Great. Let's thank Xiaodi again for a terrific talk.
Just giving you, yeah. So,
And next up, we have Stephanie Wehner, and she's going to talk about the quantum internet and the certifiable road ahead.
Thanks for inviting me. It's a pleasure to be here. I'm going to go into a different direction now. So we talked a lot about kind of quantum computing. So I will talk about quantum internet. And I guess because I gathered actually, especially in the last 2 days, that even to some of the quantum people, it's not totally clear kind of what we want to achieve here. I want to give a bit of an overview. But to put this a little bit into perspective, I actually would first want to ask you a question, which is, who can tell me what happened on this day? 29th of October, 1969. All right, well, I can tell you. Usually people say the moon landing, but no. So in fact, at this day, the first message was transmitted over, I guess, what is now called the internet, which at this point in time was extremely small. And these people here, actually, Charles Klein was at this point a grad student in Los Angeles who communicated to Stanford. You can see they worked hard, like 10:30 in the evening. And they sent the first message. And I'll tell you a bit how this went. In fact, to check, they called each other on the phone. So they typed in a letter in Los Angeles and they said, "Did you see the L?" And they got a reply saying, "Yes, excellent, we see the L." So they typed the O and they asked on the phone, "Did you see the O?" And the reply comes from Stanford saying, "Yes, we see the O." It's already 2 letters. So then they typed the G and the system crashed. So you can sort of see that obviously a little bit has happened since kind of the first message was transmitted over the classical internet. Actually, several hours later, they succeeded in transmitting the entirety of login. And the internet is quite pervasive today. But you can sort of think that kind of with the quantum internet, we are maybe at the brink of kind of a similar situation as we see here. So for example, in the Netherlands, we are trying to set up I guess currently we are on track, a sort of demonstration network between 4 cities in the Netherlands by the end of 2020. Okay. So I'll tell you here something about the efforts at QTech. There's Ronald Hansen, who is an experimentalist who works mostly on kind of connecting these quantum processors. There's Tim, who mostly works on the local quantum processors. David Elkos works quite a lot on simulations recently, which I'll tell you a bit more about later. And Slava kind of works on the physics of these kind of processors. And we also work quite closely with kind of an engineering team at TNO. And they do some engineering things for us. So this is our project manager who does this for us. For example, they do kind of wavelength conversion for us to connect. All right. So this will be over the kind of Dutch telecom network, actually of the Dutch telecom KPN, who kind of has fiber to connect these cities. All right. So someone actually asked me yesterday at the dinner, and I realized maybe I should explain a little bit kind of what are the elements of a quantum internet. So this is obviously a cartoon, but you can think that a kind of quantum internet is not so different from a classical internet. And then the objective is to kind of connect small, meaning a few qubit quantum processors over potentially long distances. So you can think that evidently we have sort of quantum processors somewhere, like your laptop, that are attached to fiber. And then the objective is to kind of enable long distance transmission. And this can be achieved on the ground by something called a quantum repeater. I don't have time to talk about how that works. Or, for example, also by satellite to kind of bridge very large distances. Okay. So you can sort of see that there's several elements that one might want to optimize here. For example, like repeaters to go maximum distance, and also some capabilities of these end nodes. Okay. All right. So I wanted to tell you a little bit kind of what is the state of the art actually of the, say, quantum internet. And so we actually work on ground-based efforts. But like I said, to bridge ultra-long distances, there was very cool results recently from a group in China that distributed entanglement over the distance of 1,200 kilometers through space, which is pretty cool. All right. So on the ground, communication over telecom fibers has not been done over long distances. I should say that sort of some quantum protocols have been implemented, chiefly, I guess, mostly the most famous one, namely quantum cryptography. So there's a procedure for exchanging encryption keys. So this has been implemented at short, meaning around 100-kilometer distances. You can buy such boxes and kind of attach them. And also various other kind of protocols have been implemented at short distances. So kind of the ground challenge is, I guess, to bridge very large distances, of course. You might also kind of Google around on the internet and learn something about a quantum network in China. For example, this one, which is actually on the ground. And this is what's called a trusted repeater network. So here, the only kind of application that can be performed is called quantum key distribution. So the objective is to exchange an encryption key between Shanghai and Beijing. And, well, I've just told you that currently we can only do 100 kilometers on the ground. This is evidently more than 100 kilometers. So the way that kind of trusted repeater networks work is that, say, if Alice and Bob want to communicate over long distances, they use an intermediate party, say a trusted repeater, and Alice generates a key with a trusted repeater generates a key with Bob, and this, provided that they kind of trust the trusted repeater, allows them to do an end-to-end encryption. So I guess we usually know how this ended. So this is obviously not kind of the desirable situation. So the goal, of course, is to go beyond that and really do end-to-end qubit transmission. Okay. Right. So there's obviously a question kind of on how to go beyond kind of this trusted repeater setting on the ground. And we actually had a lot of discussions about this, how this can ever work. Here, this is actually from last August, where we did a lot of discussions of what we want to do. In particular, we had a lot of discussion, and this is maybe sounds kind of weird, is what is actually important to achieve. Okay, so what is a quantum internet, and what do we want to optimize for? So you can think about the capabilities of the end nodes, like how many qubits should they have, how important is storage, and you can think about the capabilities of the repeaters, like how to bridge sort of long distances, and of course they should sort of kind of fit together. All right, and you can also ask yourself, well, how do we actually test that it worked after we kind of set up something outside? Okay. So I don't have to talk time to talk about all of these things, obviously, but I want to now actually talk a little bit about what do we actually want to achieve here. Okay. So Ronald Hansen and my experimental colleague and I had a huge number of discussions on this, and we have actually now defined sort of some, say, series of functionalities. And you can think that like each sort of stage of a quantum internet does give you a well-defined sort of set of extra functionality at the expense of course, ever-increasing experimental difficulty. So you can think that where we are now is kind of these trusted repeater networks. So these kind of exist, but they're kind of, I guess, a bit trivial. So the next kind of thing that one might want to do is what we call a prepare and measure network. And this maybe also gives an indication of really that this being somewhat simpler than, say, quantum computing. So basically you can think of this network, prepare and measure, of having the capability of sending and measuring single qubits. Okay? So this means that any two nodes in a network, any node can kind of prepare an arbitrary qubit, transmit it to the other node, and they can perform an arbitrary measurement. Okay? And post-selectant means that kind of the receiving node either kind of manages to perform the measurement or declares that the state is lost. Okay. So as long as the kind of probability of post-selection is not too large, in fact, this already allows you to do quantum key distribution. Okay. Yeah. Yeah, so maybe to be clear, so note that kind of here, like you want this functionality between any end nodes in the network, okay? And of course, like how difficult this is to realize, yes. Right, even classical transmission over short distances can be complicated. So like, of course, how difficult it is to realize this depends also on the extent of your network, right? So if you're only at 100 kilometers, then, I mean, this is possible, end to end, if you even have some kind of optical switch, for example. So here, I'm only talking about kind of the application-driven functionalities, not how they are realized. Okay, this is kind of an important distinction. All right. You can get a little bit more complicated and actually now ask that we can generate end-to-end entanglement between any two nodes in the network. And now we have a slightly larger demand in the sense that we want this end-to-end entanglement not to be post-selected, but we want it to be deterministic or heralded. So heralded simply means that I have a signal that says I've made entanglement that is independent of what happens on the local nodes. Okay. All right. You can also imagine that kind of you have quantum memory networks, and this kind of becomes a little bit more complicated. And we've defined it in such a way, of course, you may have more qubits, but that you can generate EPR paths. So you have all the functionality from below. You can prepare at least one qubit in Scylla. You can measure any qubits at the node. You can have an application of an arbitrary unitary. And you have some storage time. And here the storage time of interest is defined by the maximum time that it is necessary to send classical information from one node to the other. So note that also kind of what this means here depends on the diameter of my network. And of course, kind of the number of rounds of communication that I want to achieve. Okay. So maybe importantly is that here we do make absolutely no demands on this being kind of fault tolerant in any sense. Of course, you might imagine that somewhere in the very far away future, we also have fault-tolerant quantum processors in full quantum computers that might also get attached to the network. Right. But, okay. So we are aiming to go up to here, namely kind of quantum memory networks. And having, of course, defined sort of series of functions now gives us a guideline for, say, protocol design. And also for tests. So this is one of my students, Victoria, and she's currently kind of working on, say, a certain test suite that you can sort of run to say, okay, if I've passed all these tests, then I kind of am in this particular stage. Okay. All right. So let me now say a little bit kind of what quantum networks can do. So this is not a kind of exhaustive list. But there are several applications known of quantum internet that kind of go beyond quantum key distribution. So the most famous one, like quantum key distribution, can be realized in this prepare and measure stage. There's a few other tasks here, for example, certain two-party crypto tasks like identification and position verification and some other protocols that fit in here. Entanglement distribution allows you to realize something called device-independent protocols. I guess a lot of you are quantum, so you know what that kind of means. Maybe for everyone else, this means that you don't need to trust the quantum devices. So even if I kind of buy it from somewhere else, I can nevertheless use it to achieve security in my protocol, provided I trust the classical device. Kind of in quantum memory networks, you can see that one can do a lot more now. And there's all kinds of protocols for, like, I guess, at least clock synchronization over limited time that have been proposed here. Maybe most interestingly, I would like to mention that there have been protocols proposed kind of for quantum communication to solve certain problems in distributed systems. And someone yesterday also asked me kind of what this exactly means. So for the physicists here, let me give you a cartoon of quantum computer science distributed systems. So it's often important to synchronize resources in a network or to marshal access to resources. And I guess a cartoon version of such a problem is, imagine that kind of you have money in a bank. It's, of course, redundantly stored on some backup servers. Let's assume that you're rich, you have $1 million on your bank account. You withdraw the money, and the system crashed while you withdraw. So now server 1 says you have $1 million, the other one says that you have $0. So this is not such a desirable kind of situation. So people in computer science have thought a lot about this, I guess for the physicists here. And there are all kinds of advantages known in the quantum domain for solving such tasks. Maybe the last thing I want to mention, kind of if you really had large quantum computers attached, people have also kind of proposed, for example, Wehner, like protocols to save in communication and not in computation time. But then we really kind of need much more qubits. So I want to give you some kind of state of the art. So the system that we are using, I guess, in Delft is the same that we've used for this kind of loophole-free bell test some years ago. And I just give you some kind of numbers, which are partially projected. This one is a projected one. So these nodes have around 6 qubits. This may seem very few from a quantum computing domain, but it's actually a lot for quantum network application. This is kind of the current storage time. And this is an entangling rate. So how quickly can we generate entanglement between these network nodes? There's, of course, all kinds of other people who have thought about these things. There's also some groups in the US who use a similar system, for example, at Harvard and MIT. There's people who used to do this in ion traps, like Chris Monroe, and also in Europe, for example, Tracy Northrop, who we also work with. And there's a number of other kind of approaches. Okay, so Krista, I asked Krista, like, who's going to be at this talk? Are they going to be like quantum people? Are they just going to be classical people, or who are they? And so she said, okay, there's going to be mostly people from the quantum architectures group. So I actually decided to talk about a very quantum thing, I guess, for the quantum people here, even though somehow a lot of work that we've done recently is rather classical and not so much quantum, and I'm going to talk a little bit about this afterwards, actually. So I want to show you kind of one procedure now, which relates to estimating the capacity of a quantum channel. Okay? Let me kind of ask what this question is. It is motivated by the following. So let's say that Alice and Bob are connected by a direct quantum communication channel, and they use a quantum repeater. You want to have a test or some measure that tells you that kind of this repeater actually improves the situation over having no repeater. Okay? So it would be nice if the repeater would be better than having no repeater. And there's, of course, all kinds of measures one could kind of think of, but one of them is, in fact, motivated by, I guess, information theory, namely the capacity of a channel. So there's a number called the capacity associated with all kinds of communication channels. And in particular, one can consider the capacity of the direct communication channel. The capacity is basically the number of bits transmitted divided by the number of channel uses, maximized over all possible encoding and decoding schemes. And this also can be defined in the quantum case for the classical people here. Okay. All right. So of course, one could now do an experiment that says, I want to demonstrate that the rate of communication with the repeater is larger than the capacity of the direct connection. And this can be done. For example, one way to do this, kind of for sending key, so this is one of my students, Kenneth, who's also derived some bounds for capacities for producing keys, for quantum, the private capacity for producing key. Is basically you compute this or compute a bound on this, and then you implement a quantum key distribution scheme to observe that the rate of producing key is larger than the rate of, say, that you calculate from the direct communication channel. So the question is now, can you do something similar for sending qubits? So it is actually harder to send qubits, meaning the quantum capacity is in general smaller than the private capacity. So can we make a test where we can also demonstrate that the repeater improves your abilities to send qubits and not just to produce key? Okay. And so for this, of course, first you want to know something about the capacity of the direct communication channel. There's all kinds of things known about that. There's also, I want to point out, some very nice work that studies this in the finite n regime, so not using infinitely many channel uses, but a finite number of them. So this we can sort of do or kind of look up in the literature. And then we want to, of course, now do a test to demonstrate that the rate at which we can send qubits is larger than this capacity of the direct connection. Okay, so let me paint a cartoon. Okay, if I have a quantum memory or quantum communication channel, so communication channel going from the left to the right, I might, of course, use an encoder and a decoder. Okay? Like David, for example, gave you such things for fault tolerance schemes. So you can think that here we only want to compute the identity. We never want to do any gates. We only compute the identity. And we would like to know how well can this be done. Okay? So this is a given here. And we want to know how well could we send information given any possible encoder and decoder. So I should say that this can also be used not just to test physical devices, but this could also be logical qubits, okay, if this is kind of a memory, but whichever way you want to use it. Okay. So some attempts is, of course, we could implement a quantum error correcting code. We just take our qubit, we encode it, we send it across, we decode it, and we demonstrate that we can have achieved good transmission of some fidelity, and we conclude that we can send information at a certain rate. So this, of course, means that we have to implement a quantum error correcting code. Okay? So this would require that we have quantum computers on the left and the right, actually decently large, that can encode a certain number of qubits. You could also say, let me fully characterize the device. Or maybe I can estimate the diamond norm or other measures. Okay? This, of course, would be nice. But first of all, we maybe have to make some assumption then at least if I send many times or have memory, say many memory pieces, maybe I want to assume that they're all the same. But this is actually almost never of that form. So any communication channel or physical device usually has some kind of memory. And second of all, there's some bad news in the sense that even if you would know M, in fact, we don't immediately know what the capacity actually is. Okay, there's bounds known, but we don't in general know that. So the goal is that we want to achieve here is we want to estimate this quantum capacity directly. It should work for any device, in particular devices also that have correlated noise. And we only want to do extremely simple operations. So to be very specific, okay, let me now say a little bit what exactly we want to estimate by this capacity. And I have now not assumed that here we have kind of what's called IID noise. So the noise would be the same on each qubit, but basically it's some kind of giant noise channel, arbitrary correlated noise. I don't know what it is. Okay. So we have an encoder and a decoder, which doesn't actually exist, but we want to say if we had this encoder and decoder, how could we do? And we're now interested in the following quantity, which is known as the single-shot capacity of a quantum channel. Okay? I guess there's not some quantum people here, so not everyone's quantum, but bear with me. So what does this quantity measure? So let's think first about the fidelity of transmission. So if I started with a state phi, I could think about what happens if I encode that state, then kind of noise process is applied, I decode, and then I'm interested in the overlap, so the fidelity between the input state and whatever comes out from my decoding scheme. So we want to be kind of smart about that, okay? Like, so I'm allowed to use kind of any possible decoder and encoder, but we're also sort of a little bit kind of pessimistic in the sense that I'm interested in the worst case of this fidelity, okay? So I'm looking at the worst case of sending transmission. And of course, kind of say the worst case fidelity, kind of maximized over all possible encoding and decoding schemes, I can think about, well, how large is my input space that I can actually kind of transmit? And so the single-shot fidelity is nothing else than the log of kind of this maximum input dimension, such that the worst case fidelity is not smaller than 1 minus epsilon for some fixed epsilon. Okay. Of course, for example, if epsilon is 0, so I don't have any demands, then of course my capacity is very high. If my fidelity is my worst case fidelity is extremely close to 1, okay, then I can send less information at that rate. Okay. All right. So the goal is now to estimate this thing. Okay. And maybe to be clear, I now want to estimate this using only single qubit preparations and measurements. Okay. I allow you to only kind of prepare and measure single qubits at a time. And the objective will be that from whatever data we've measured, we'll apply some function and we'll get a bound on this capacity. So maybe to say one thing, but the objective here is only to estimate a lower bound, okay, and not an upper bound. An upper bound cannot be obtained if you allow arbitrarily correlated noise, okay, because it can kind of conspire against you to do something else in every single instance to kind of trick you into believing that the capacity is low when actually it might be high. But actually for all applications, it is enough to show that the capacity is large so that the channel is good, not that the channel is bad. Okay. Right. So there's a very simple protocol actually, and that basically kind of uses ideas from quantum key distribution that is based on the idea that if we can transmit in two complementary bases through a channel, then we can also send qubits very well. Okay. So basically what we do is we just kind of randomly prepare eigenstates of sigma x and sigma z. We do this very many times, and we measure it in the same basis, and we measure the error rate of sending information in the x basis and the error rate of sending information in the z basis. So the kind of procedure here is very simple, and then of course there's some kind of theoretical analysis, which I'm not going to talk about. And from this one can conclude that either the data is highly untypical, of course this is a statistical statement, we have a precise statement of course, or indeed the quantum capacity is large, large meaning like the number of transmissions that we've done here, the preparation quality, so kind of for perfect x and z this would be 1. If my bases are not perfect but somewhat more close together, this kind of becomes smaller. This is the binary entropy of the error rate of x, and this is the binary entropy of the error rate of z. Okay, I'm putting under the hood here like all kinds of finite size effects, but you can look here for the formal theorem and some actually tests that we've also done using a superconducting qubit. Okay, so this is nice because we can now actually just using single qubit preparations and measurements also test whether kind of a quantum repeater repeats qubits and not just key. So of course there's various analysis that has been done, and on the basis of this one can do an analysis like which regimes do I have to be in order to kind of beat these bounds. And such things we have done with my colleague Ronald and also with my collaborator Tracy in Innsbruck. I'm rapidly running out of time. Well, I'm only getting to this. But I will be very brief here. Okay. So given that we actually have this excellent opportunity to kind of set up this demonstration network in the Netherlands, we have decided that this will be a universally programmable quantum network. Okay. In particular, we want to have the capability to actually execute kind of any sort of quantum network protocol on these kind of quantum devices. And you can now think actually about how would I now go about programming a quantum network. And I guess for the physicist here, there's sort of an additional complication in the sense that I don't program just on my local computer. But I have at the bottom the hardware. Okay, this kind of changes qubits. I have somewhere at the bottom some application, like a protocol that exists on paper where it says Alice sends a qubit to Bob, and then Alice measures this, Bob measures that. But there's, of course, some classical communication required between Alice and Bob to make that happen that sort of needs to match together with what happens down here. Okay. The same actually goes also if we wanted to kind of route qubits around, but I'm not going to talk about that here. So in order to kind of think about this, we have realized a network simulator. Actually, it is designed solely for the purpose to explore how to kind of program these quantum network applications. And it essentially sort of replaces this hardware by, say, a virtual quantum node, like a little client-server program you can actually install on different laptops, and they can talk to each other by classical communication, kind of simulating this quantum communication. So I will maybe say a little bit on how this kind of works. Actually, I will not say a lot how this works, but I will maybe say how it is different than kind of a kind of standard simulator. So in fact, this can use actually any sort of simulator as a backend that kind of can talk to Python. We actually use Qtip, but you can also use maybe Project Q or others. I guess it's very easy to change that actually. And what it allows you to do is, well, you can start up, say, these kind of virtual quantum nodes. You can also kind of have sort of classical program, basically. And so you can have classical communication between these two, and you can access, as you would, I guess, with hardware, say, create new qubits, measure qubits, send instructions to perform these things, and also send instructions to send qubits to other nodes in the network. Indeed, so they talk to each other classically. I will not say kind of how the simulator works, but I will want to say that one thing that makes it different, kind of that simulating things locally. Okay, so of course I can have a locally simulated quantum register, say using Qtip, whatever. Okay, in there I can have qubits. Let me make some qubit objects. Okay, they can be somewhere in this register. And I want to represent them using virtual qubits that kind of are attached to these qubit objects. Now, of course, one thing that kind of a quantum network does is that it allows two nodes to have two entangled qubits. Okay? But the whole point of entanglement is that I cannot represent it by local classical information. So for this reason, kind of I need to think about if these kind of two network nodes have qubits, where are they actually simulated? So this is essentially a distributed simulation. So note that also this node may locally have a simulated quantum register with some qubits, and maybe the virtual qubit is actually simulated over here. So kind of the challenge in the simulation, or actually the only challenge in the simulation that distinguishes for a normal one, is to basically perform these distributed simulations and keep track. So if you, for example, make an entangling gate here, we now need to decide where these qubits are going to be simulated, here, here, or there. So we have not yet released this, but I have, however, given it to some of my colleagues in software engineering. They're now playing around with kind of programming this, which is actually pretty cool. So I enjoyed it. Right. So let me maybe say one more thing, which I guess is quite a computer science question. But if you think about kind of how to sort of make a quantum protocol and work in an actual network, you will also realize that there's an essential difficulty, I guess, if you've ever thought about kind of network protocols or protocol stack, is that there's many of them, but I'll give you one simple example. So if you transmit information over a classical network, there's a very convenient thing in the sense that you can have a header that says, like, where does the packet come from, where does it go to? And conveniently, the data is, of course, also classical. Okay? So the whole thing, header and classical data, can kind of travel across the network together. Okay. So this is kind of not the case here, okay? Because the qubits are here, and kind of classical data travels over the kind of classical network, kind of this control information. So together with actually one of Ronald's students and one of my students, we're currently working on various iterations of kind of a stack that prevents this question. The first one being, say, a classical quantum combiner. So after this, you will only see, will have matched the header information to the qubit information. So they are again together. And based on this, you can then run all kinds of other protocols to keep track of entanglement on top of that. Okay. Right. So I want to mention a few other things in Delft. So in fact, we can now distill entanglement, thanks to my excellent colleague. David actually, so together with some people from TNO, we now have a different kind of simulator actually that can be used to test really the performance of protocols, also repeater schemes, which is a discrete time event simulation. So what does this mean? So in a network protocol, timing delays are extremely important. And I've just, maybe you remember a long time ago, I said the coherence time is like 1 second, not very long. But this means that the time that it takes for messages to travel now is crucial. And with this simulator, we actually want to explore certain designs of repeaters and nodes, and also the placement of these nodes, for example, in the Netherlands, such that you can have end-to-end qubit transmission at certain fidelities. Okay. I can talk to you more about this. It's actually quite fun. This relates to sort of transforming states in a network. If you want, I can tell you about it. And also, of course, there's interesting applications, for example, powered by my student, Jeremy. So I think I'm officially out of time now, but there's kind of too many questions, okay? So with these stages, there's now a question kind of what are actually the best tests to check that I'm at that stage. It would be extremely interesting, of course, to find protocols in the more lower stages. Okay? So I've given you all these kind of tasks that can in principle be solved by a quantum network, and maybe there's exciting new ones. But of course, the objective is now to realize a protocol, to find a protocol to solve a particular task in as low a stage as possible. We've also estimated the quantum capacity. I'm quite sure this might not be the most efficient way to go about this, but there might be others. And yes, you can try this once we release it. So if you want to send login in 2020, I will also answer the question from the panel discussion yesterday. Where do you go if you want to learn about quantum technologies? I'm evidently totally biased, so we actually have a master program in that. And we also often have open positions, which you can check here. All right, thank you very much.
Great, thank you, Stephanie. Other questions? Great, Xiaodi.
Yeah, thanks for a nice talk. So actually, I have a question about the program network part. So actually, I want to ask, what's the let's say the first goal of the project? It's like any like killer application that you want to achieve with that kind of simulation, or anything maybe you have in your mind but you haven't talked in this talk.
Well, so this. So the objective that we want to achieve here, actually there's, I guess, two objectives. One of them really relates to how do you program a quantum network, okay? This may, it is not so true. I mean, even if you think about a totally trivial protocol, which is like this, Alice and Bob generate an EPR pair. They measure it to generate a random coin. I don't know why, but let's say they do. Already this kind of, if you think about how do you go from this description to connecting it with the kind of qubits in the hardware, is complicated. You have to kind of know, for example, which of these qubits in my hardware device is the right qubit. How do these things kind of fit together? Maybe you even want to be able to run several applications at the same time. It's quite complicated. And in order to explore that, we've generated this simulator. And in fact, the first object, I guess there's, on the one hand, we are exploring this kind of protocol stack, like this classical quantum combiner. And on the other hand, we are actually using that to then sort of investigate how to program really applications using that stack. I think this is something actually that to some extent you have to try, which is why we made this simulator.
I see. Thank you.
Great. Well, lunch is ready. Let's thank Stephanie again for a wonderful talk. Let's resume at 1:15. And if anyone is looking for some vitamin D, it's a beautiful day outside. There are tables right outside the conference center with chairs, and you're welcome to take your lunch outside rather than just stay in this room. So lunch is here on the left, and come back at 1:15. Thank you.